Hello everyone, my name is Amit Khan. In this video, I will discuss about data converters. It is the topic of digital electronics. Data converters means analog to digital converter and digital to analog converter. So first we will study digital to analog converter, that is D2A converter. It is also known as DAC, D2A converter is a system that converts a digital signal into an analog signal. There are mainly two types of methods that are commonly used for digital to analog conversion. They are weighted register method and R2R ladder network. So first we will study the binary weighted register type DAC. A weighted register DAC produces an analog output which is almost equal to the digital or binary input by using binary weighted registers in the inverting adder circuit. In short, a binary weighted register DAC is called as weighted register DAC. The circuit diagram of a 3-bit binary weighted register DAC is shown in the following figure. It is a 3-bit binary weighted register, so we can see in the diagram that B0, B1 and B2, so 3-bit binary weighted register DAC. Now recall that all the bits of a binary number can have only one of the two values, either 0 or 1. So let the 3-bit binary input is B2, B1, B0. Here the bits B2 and B0 denote the most significant bit, that is LSB, and MSB, and least significant bit LSB respectively. So B2 is MSB and B0 is LSB. The digital switches shown in the figure will be connected to ground when the corresponding input bits are equal to 0. Similarly, the digital switches shown in the above figure will be connected to the negative reference voltage minus VR when the corresponding input bits will be equal to 1. In the above circuit, the non-inverting input terminal of an op-amp is connected to ground. That means 0 volts is applied at the non-inverting input terminal of op-amp. So according to the virtual short concept, the voltage at the inverting input terminal of op-amp is same as that of the voltage present at its non-inverting input terminal. So the voltage at the inverting input terminal's node will be 0 volt, and the nodal equation at the inverting input terminal is given, that will be V naught equals to VR into RF divided by R into B2 by 2 to the power 0 plus B1 by 2 to the power 1 plus B0 by 2 to the power 2. So substituting R equals to 2 into R into F, we get V0 equals to R by 2, VR by 2, B2 by 2 to the power 0 plus B1 by 2 to the power 1 plus B0 by 2 to the power 2. So the above equation represents the output voltage equation of a 3-bit binary weighted register DAC. Since the number of bits are 3 in the binary input, we will get 7 possible values of output voltage by varying the binary input from 000 to 111 for a fixed reference voltage VR. So we can write the generalized output voltage equation of an n-bit binary weighted register. The equation will be V naught or V0 equals to VR by 2, Bn minus 1 by 2 to the power 0 plus Bn minus 2 divided by 2 to the power 1 plus Vn B0 by divided by 2 to the power n minus 1. The disadvantages of binary weighted register DAC are the difference between the resistance values corresponding to LSB and MSB will increase as the number of bit present in the digital input increases. It is difficult to design more accurate resistors as the number of bits present in the digital input increases. Then comes R2R ladder type DAC. In the diagram you can see the R2R ladder type DAC. It overcomes the disadvantages of binary weighted register DAC. As the name suggests, R2R ladder DAC produces an analog output which is almost equal to the digital input by using R2R ladder network in the inverting adder circuit. The circuit diagram of a 3-bit R2R ladder DAC is given in the figure. Then recall that the bits of the binary number can have only one of the two values, either 0 or 1. So the 3-bit binary input is B2, B1, B0. B2 is MSB and B0 is B0 is the LSB. The digital switch is shown connected to the ground when the corresponding input bits are equal to 0. Similarly, the digital switches shown in the figure will be connected to negative reference voltage -VR when the corresponding input bits are equal to 1. It is difficult to get the generalized output voltage equation of R2R ladder DAC, but we can find the analog output voltage of R2R ladder DAC for individual binary input combinations easily. The advantage of R2R ladder DAC is it contains only two values of resistor, R and 2R. So it is easy to select and design more accurate resistors. Another advantage is if more number of bits are present in the digital input, then we have to include required number of R2R sections additionally. So due to the above advantage, it is preferable over binary weighted register DAC. Then comes what are the specifications of DAC. The specifications are reference voltage, resolution, linearity, speed, settling time, error. It is also given that resolutions means it increases, the number of bit increases. Settling time is the time for DAC to come within 0.5 LSB of new voltage after binary change. Then comes what are the applications of DAC. Applications of DACs are it is used in digital oscilloscopes, voltage controlled amplifier, signal generators, music players, TV, etc. Then comes analog to digital converter, that is A to D converter or ADC. What are the types of ADC? The ADCs are parallel comparator or flash type, dual slope type and successive approximation type. So first one is the parallel comparator or flash type ADC. The flash type ADC, also known as direct conversion ADC, is a type of A to D converter that uses a linear voltage ladder with a comparator at each rung of the ladder to compare the input voltage to successive reference voltages. Often these reference ladders are constructed of many resistors, but in modern implementations shows that capacitive voltage division is also possible. The output of these comparators is generally fed into a digital encoder which converts the inputs into a binary value. The collected outputs from the comparators can be thought of as a unary value. A 2-bit flash analog to digital converter is given in the diagram. Then comes successive approximation type ADC. The main part of the circuit is the 8-bit SAR, whose output is given to an 8-bit D2A converter. We can see that in the circuit diagram or block diagram of the successive approximation type ADC. We can see the 8-bit SAR. Its output is given to the 8-bit D2A converter. The 8-bit DAC is given in the figure. The analog output VA of the D2A converter is then compared to an analog signal V in. So we can see the analog voltage output of VA and the analog input V in both are fed to a comparator. The output of the comparator is a serial data input to the SAR. You can see in the diagram the output of the comparator is a serial data input to the 8-bit SAR. Till the digital output of the SAR is equivalent to the analog input V in, the SAR adjusts itself. The 8-bit latch at the end of conversion holds onto the resultant digital data output. We can see that in the diagram also. At the start of a conversion cycle, the SAR is reset by making the start signal S high. The MSB of the SAR Q7 bit is set as soon as the first transition from low to high is introduced. Then the output is given to the D2A converter, which produces an analog equivalent of the MSB and is compared with the analog input V in. If comparator output is low, then the D2A output will be greater than V in and the MSB will be cleared by the SAR. If the comparator output is high, then the D2A output will be less than V in and the MSB will be set to the next position, that means Q7 to Q6 by the SAR. So according to the comparator output, the SAR will either keep or reset the Q6 bit. This process goes on until all the bits are tried. After Q0 is tried, the SAR makes the conversion complete signal. So the conversion complete signal, CC signal, becomes high to show that the parallel output lines contain valid data. The CC signal in turn enables the latch and the digital data appears at the output of the latch. As the SAR determines each bit, digital data is also available serially. As shown in the figure, the CC signal is connected to the start conversion input in order to convert the cycle continuously. Then comes dual slope type ADC. We can see the diagram of a dual slope type ADC. It is in dual slope type ADC, the integrator generates two different ramps. One with the known analog input voltage VA and another with the known reference voltage V reference. So it is called a dual slope A to D converter. We can see the integrator circuit here in the diagram. Here the binary counter is initially reset to 0000. The output of integrator reset to 0 volt and the input to the ramp generator or integrator is switched to the unknown analog input voltage VA. The analog input voltage VA is integrated by the inverting integrator, and so it generates a negative ramp output. Then the output of the comparator, if it is positive and the clock is passed through the AND gate, then if the negative ramp continues for a fixed time period T1, which is determined by a count detector, at the end of the fixed time period T1, the ramp output of integrator is given as V minus Vs equals to minus Va divided by Rc into T1. When the counter reaches the fixed count at time period T1, the binary counter resets to 0000 and switches the indicator input to a negative reference voltage minus V reference. Now the ramp generator starts with the initial value minus Vs and increases in positive direction until it reaches 0 volt and the counter gets advanced. So when Vs reaches 0 volt, the comparator output becomes negative, that means logic 0, and the AND gate is deactivated. Hence no further clock is applied through AND gate. Now the conversion cycle is said to be completed, and the positive ramp voltage is given by minus Vs equals to V reference divided by Rc into T2, where V reference and Rc are constant and time period T2 is variable. The dual ramp output waveform is shown in the figure. We can see the dual ramp output in the diagram. So the unknown analog input voltage VA is proportional to the time period T2, as because V reference is a known reference voltage and T1 is predetermined time period. So the actual conversion of analog voltage VA into a digital count occurs during time T2. The binary counter gives the corresponding digital value for time period T2, and the clock is connected to the counter at the beginning of T2 and is disconnected at the end of T2. So the counter counts digital output as digital output equals to counts by second into T2. So digital output equals to count divided by second into T1 into VA divided by V reference. So for example, consider a clock frequency is 1 megahertz and the reference voltage is minus 1 volt. The fixed time period is T1 is 1 millisecond, and the RC time constant is also 1 millisecond, assuming the unknown analog input voltage amplitude as VA equals to 5 volt. So during the fixed time period T1, the integrated output VS equals to minus VA divided by RC into T1, that is equals to minus 5 divided by 1 into 1, that is equals to minus 5 volt. And during the time period T2, the ramp generator will integrate all the way back to 0 volt. So 2 equals to Vs divided by V reference into Rc, that is equals to 5000 microsecond. So a 4-bit counter value is 5000, and by activating the decimal point of MSD 7-segment display, the display can directly read as 5 volt. Here's the comparison between the different types of ADC. We can see the dual slope, its speed is slow. The speed of successive approximation is medium, and flash type, the speed is fast. Its resolution for dual slope is 12 to 20. Successive approximation is 8 to 18, and flash type is 4 to 12. Noise immunity is good for dual slope. Noise immunity is little for successive approximation, and noise immunity is little for flash type. Cost of dual slope is low, cost of successive approximation is low, and cost of flash type is high. The specifications of ADC are analog input voltage range, input impedance, accuracy, quantization error, resolution, conversion type, format of digital output, temperature stability. These are the specifications of ADC. The applications of ADC are digital storage oscilloscope, microcontrollers, cell phones, computers, digital signal processing, etc. Thank you for watching this video.